So far we have discussed gears with reference to a pair of gears. But very often the input and the output shaft are connected by more number of gears. And such a combination of gears to connect the input to the output shaft is called a gear train. Gear train is nothing but a combination of gears. Which are used to connect the input shaft to the output shaft. Now a gear train may consist of all types of gears like spar. The same gear train may consist of a few spar gears, few helical gears, bevel gears, like that. So a combination of gears which is used to connect the input to the output shaft called a gear train, and a gear train may consist of all types of gears or maybe only one type of gear. Now, unless otherwise specified, we will always assume that all gears in a train have same module. There are exceptional gear trains where all gears do not have the same module, but in general all gears in a gear train will be assumed to have the same module. Which means if two gears 1 and 2 are in engagement, then their speed ratio will be given by the inverse ratio of the number of teeth. This is the angular speed of gear 1 and gear 2, and these are the number of teeth on gear 2 and gear 1. It is an inverse ratio. As we know, if this is external gearing, then omega 1 by omega 2 will have a negative sign, and if it is internal gearing, then omega 1 by omega 2 will have a positive sign. That we have to keep track of. Now the question is, why do we need more number of gears to connect a particular input shaft to the output shaft? There may be various reasons for that. For example, the orientation of the input and output shaft. That may dictate that you need to have more than 2 gears. Orientation and placement, the spatial location. Orientation and spatial location. The input and output speed may vary by a wide margin. That is, the ratio of the input and output speed is very much different from 1. It is much larger than 1 or much less than 1. In such cases also, we may have to use a gear train. That means the speed ratio of the input to the output speed widely different from 1. If the speed ratio is say 60, then we cannot get by using only a pair of gears to connect the input and output shaft to create a speed ratio of 1 by 60 or 60. So under such situations we need gear trains. In this lecture we will do this analysis of gear trains. That means if a gear train is given, we should be able, and the number of teeth on the gears are specified, we should be able to find out what is the speed ratio between the output and input shaft. Now I will show you a figure of a particular gear train which consists all kinds of gears. This figure shows a typical gear train. This is the input shaft which is rotating in this direction, and the output shaft is located here, whose axis is perpendicular to the plane of the board or plane of the paper or plane of the screen, that is going like this. So to connect these two shafts, the input and output shaft, and to get a particular speed ratio, we may need, as we see, a pair of bevel gears, then a pair of spiral gears or cross helical gears, which are connecting these two skewed shafts, and a pair of spur gears to connect this shaft to this shaft. So this pair of bevel gear connects these two shafts. This shaft and this shaft, which is skewed, are connected by a pair of cross helical gears, and these two parallel shafts are connected by a pair of spur gears. So this shows you an example of a typical gear train. In this lecture, we shall analyze gear train, and we start our discussion with classification of gear trains. Before analyzing gear trains, let me first classify different types of gear trains. So gear trains classification. Gear trains are normally classified under three headings, namely simple, compound, and epicyclic. These are the three normal forms of gear train: simple, compound, and epicyclic. Simple gear train is that gear train where on each shaft there is only one gear. There is the input shaft, there is the output shaft, and there may be several or one intermediate shaft connecting the input to the output shaft, but on each shaft there is only one gear. So simple gear train has one gear on each shaft. For example, suppose this is one gear, mounted on this shaft, which is the input shaft. This is connected to another gear which is on another shaft, and that gear is mounted on another shaft, and this may be the output shaft. This is what we call the intermediate shaft. Input shaft, output shaft, and there is an intermediate shaft, and there is one gear on each shaft, and the motion from this input is transmitted to the output. Now, analysis of such a simple gear train is almost trivial. As we see here, these are all external gearing, and the number of teeth is, say, N1 on this gear, N2 on this gear, and N3 on this gear. So omega 1 by omega 2, as I said, will be minus N2 by N1, because it is external gearing and it is inversely proportional to the number of teeth. Similarly, angular speed of the intermediate shaft to the output shaft, which is omega 2 by omega 3, that will be minus N3 by N2. From here to there, again is an external gearing, so the direction of rotation changes, and in the inverse ratio of the number of teeth. If I multiply these two, we get the input shaft, which is omega 1, input speed, which is omega 1, divided by omega 3, which is the output speed. If I multiply these two, omega 2 cancels, and here N2 cancels, and minus into minus gives me plus, so it is N3 by N1. So what we see, that the direction of rotation of this shaft is same as the direction of rotation of this shaft, and this shaft rotates in the other direction. And the input speed by output speed is N3 by N1, so we can get the reverse if I want output speed by input. The thing to note is that the number of teeth on this intermediate gear is of no relevance. The speed ratio is dictated only by the first gear and the last gear, the number of feet on the gear mounted on input shaft and the number of feet on the gear mounted on the output shaft. There may be several intermediate shafts, but the number of feet on those gears will be immaterial so far the speed ratio is concerned. Only the number of intermediate shafts will change this from plus to minus. Here as for example there is only one intermediate shaft, omega 1 by omega 3 is positive. Had I had another intermediate shaft, then omega 1 by omega 4 would have been N4 by N1 but with a negative sign. In this diagram we show three different simple gear trains. As we see there are four shafts in this figure. 1, 2, 3, 4. Let this be the input shaft and this be the output shaft. These are all connected by bevel gears. Now the speed ratio, as we calculated just the example we discussed before, the shafts are parallel, so it was very easy to keep track of plus or minus. At every step there is a change of sign. But here as we see the shaft axes are all intersecting and not parallel, so plus minus will be confusing. So there we have to follow, if this is the direction of rotation of shaft 1, then this is the direction of rotation of shaft 2. And this direction of rotation creates this direction of rotation for shaft 3 and that creates this direction of rotation for shaft 4. So if we want to write the output speed omega 4 by omega 1, that will be nothing but N1 divided by N4. But N1 is the number of feet on this gear and N4 is the number of feet on the final gear. The intermediate number of feet are totally unimportant. And the direction of rotation we see as we have shown in this draw. Now let me take the example of this case where again it is a simple gear train. There are four shafts and on each shaft only one gear is mounted from input to the output. As we see, this counterclockwise rotation rotates this gear clockwise, which makes this gear to rotate counterclockwise, which makes this gear to rotate clockwise. Here of course we know the output speed omega 4 by omega 1, because there are two intermediate shafts we get a negative sign N1 by N4. With one intermediate shaft we have done earlier, they rotate in the same direction, but as soon as there are two intermediate shafts we get in the opposite direction, that is a negative sign. Right, N1 is the number of feet on this gear and N4 is the number of feet on this gear. Number of feet on the intermediate gears do not matter. Very often this angular speed will write in terms of RPM and I will denote by small n. The small n refers to RPM and capital N will refer to the number of feet on various gears which are written as this subscript. Now let us come to the example of this simple gear train. Here again 1, 2, 3 and the 4 which is an internal gear whose shaft is somewhere here at the center of this gear 4. Thing to note is this is a pair of external gearing, this is a pair of external gearing, but 3 and 4 there is a pair of internal gearing. So this omega 1 creates this omega 2, that creates this omega 3, and because of internal gearing omega 3 and omega 4 are in the same direction. So here again we can write omega 4 by omega 1 is N1 by N4. Though there are two intermediate shafts, but this is plus sign because there is a pair of internal gearing as opposed to in this situation where there are all external gearing. Here 1 and 2 are external gearing, but between 3 and 4 it is internal gearing. So there is no negative sign here. So analysis of such simple chain, as I said, is pretty trivial. Now let me discuss how to analyze compound reaction and what is a compound reaction. Let me now discuss what we mean by a compound reaction. In a compound reaction, there will be more than one shaft on some, there will be more than one gear on some shaft. Either on the input shaft or output shaft or intermediate shaft, there must be one shaft in this transmission, in this gear train, where there will be more than one gear on one shaft. For example, suppose this is the input shaft, this is the output shaft, and this is one intermediate. As you see, on this intermediate shaft there are two gears. So this is a compound reaction from here to the output shaft. Now let me find out what is the speed ratio in such a compound reaction. Let the number of teeth be N1, N2, N3, N4. Because gear number 1, 2, 3, 4. Because gear 2 and 3 are both connected to the intermediate shaft, their speed will be same. That is the speed of this shaft. So we can find omega 2 by omega 1, because it is external gearing, it is minus N1 by N2. And omega 3 is same as omega 2 because they are mounted on the same shaft. So omega 3 is omega 2. And again, omega 3 by omega 4 will be minus N4 by Nc, because this is again a pair of external gearing. So if I now multiply these two, what I find, if I omega 3 by omega 4 and 4 by Nc, and this is omega 2 by omega 1, so I have to divide. So if I divide this by this, omega 2 being same as omega 3, that will cancel. So we get omega 4 by omega 1. I am dividing this by this. So omega 4 by omega 3, that becomes this, and N1 by N2 into N3 by N4. The minus minus cancels. I am dividing this by this. So N1 by N2 into N3 by N4. So this is the output speed to the input speed. The thing to note is that now the speed ratio from the output to the input or input to the output is decided by the number of teeth on all the gears. Intermediate number of teeth become relevant. For a simple reaction it was depending only on N1 and N4, but for such a compound reaction they are dependent on all the numbers of teeth on all the gears. Very often such two gears are made out of one rigid body. The gear teeth are machined on a same rigid body, the gear blank, with teeth are cut here and teeth are cut there, such that this becomes one rigid body, which again ensures omega 3 equal to omega 2. So this is how we analyze a compound reaction. This figure shows again a compound reaction. As we see on these two shafts there are more than one gear. There are two gears, one here and one there. So this gear is connected to this gear
and on the same shaft there is this gear which connects to this gear, and on the same shaft there is another gear which is connected to this gear. So from here to here the speed rotation is being transmitted through these two intermediate shafts. So this is a compound gear train. So if we say the number of teeth on this gear is N1, number of teeth on this gear is N2, number of teeth on this gear is N3, the number of teeth on this gear which is connected to 3 is N4, and this gear is N5, and on this gear, final gear, is N6. So as we see, omega 4 and omega 1 are in opposite direction. That can be seen very clearly from here to there. Then this rotates clockwise, so this rotates anti-clockwise, so this rotates clockwise. Now here what I can write, omega 1 by omega 2 is minus N2 by N1. Now omega 3 is same as omega 2, and omega 3 which is same as omega 2, I can write omega 2 by omega 4 is minus N4 by N3. Omega 2 is same as omega 3. This omega 3, let us not be confused with this. I will remove this. This is 6. In 6 I will write omega 6. This is the 6th gear. So omega 2 is same as omega 3, and then I get omega 4. And omega 4 is same as omega 5, that is the speed of this gear. So we can write omega 5, which is same as omega 4, divided by omega 6 is same as this. I write omega 6. This I write omega 4, which is same as omega 5, and this is omega 2, which is same as omega 3, and this is same as omega 5. So omega 4 by omega 6 is minus N6 by N5. Is actually omega 5 by omega 6 is minus N6 by N5, and omega 5 is same as omega 4, so I write this. Now if I multiply all this, as you see omega 2 and omega 4 cancels, I get the input by the output speed, omega 1 by omega 6, minus 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 gives me minus, and here I have N2, N4, N6 divided by N1, N3, N5. So input speed by output speed, negative sign implies they are in opposite direction, and they are governed by the number of teeth on all of these gears in this compound gear. Next we shall discuss the most difficult one, where such visualization of rotation of various gears will not be possible, and that is what we call epicyclic gear train. In the simple and compound gear trains that we have discussed so far, we saw that all the gear axes of the shafts on which the gears are mounted were fixed in space. That means the gear axes of all the gears were fixed in space. They are not moving in space, both in simple and compound gear. Whereas in epicyclic gear train, we will see that there will be one gear whose axis is not fixed in space, because that gear is mounted on an arm, and that arm is rotating and carrying the shaft of that gear along with it. In such a case, in such a gear train, if there is one such gear, we call it an epicyclic gear train. Some books call it planetary gear train.
To show you, suppose I have I have one gear here and another gear there. This gear, let me call it 1 and this gear number 2. But gear number 2 is carried by this arm which is also hinged here. That the axis of the gear 1 and this arm both are hinged to the fixed link at this junction. So when this gear chain rotates, as we see, this gear 2, the center of the gear 2 moves on this circle with this point as the center. Consequently, the axis of this gear 2 does not remain fixed in space, and this constitutes what we call an epicyclic gear chain or planetary gear chain. In fact, this we call the sun gear around which the planet gear is moving. That's why the name planetary. Epicyclic because we know if a circle rolls on another circle, then any point on this rolling circle generates a curve which is called epicycle. The curve that a point on this rolling wheel generates as it rolls around this circle is called epicycloid, and from there this name came epicyclic gear chain, as a point on this gear will generate epicycloid. Let's not bother so much about the name epicyclic or planetary. What we should note that this is a 4-link mechanism. As usual, we give the fixed link number 1, this gear let me call 2, this arm is 3, and this gear 4. So this is a 4-link mechanism. N is 4. Let me first calculate the degrees of freedom of this mechanism. If you remember, degree of freedom F can be obtained from C n minus 1 minus 2j minus h, where j is the equivalent number of simple hinges, that is j1 plus 2j2 like that, and h is the number of higher pair, n is the total number of links. Now here as we see, there is a revolute pair between the arm and gear 4 here, so j1 is 1. Here is a revolute pair, but that connects 3 links, namely 1, 2 and 3. So this is a hinge of type J2. So J2 is also 1. And between the gears 3 and 4, these are the pitch circles. Let me not draw, these are imaginary circles representing the gears. It is between 3 and 4, we have a gear tooth connection, which is a higher pair. So H is also 1 between 3 and between 2 and 4. Gear number 2 and gear number 4, they are having a higher pair between them. So if I now substitute n equal to 4, I get 9 minus j is j1 plus 2j2, that is 2 plus 1, 3. J is 3, 2 into 3, 6, minus h is 1, 2. So the degree of freedom of an epicyclic gear chain is 2. What does it imply? That we need 2 independent input speeds to fix the output speed, because it has a degree of freedom 2. Or in other words, if we give only 1 input speed, then we can get two output speeds which will be coordinated, but they will be non-unique. I can adjust both of them. They have to follow certain relationship, but they can be otherwise non-unique. So I can generate two different speeds, two output speeds from the single input speed. And that is where we use such epicyclic reaction. Now how do I analyze such an epicyclic reaction? Here, as we know, it will be very difficult to visualize the direction or rotation of various gears because this gear is not fixed in space. So let me try to make a rather mechanical method, develop an analytical method to follow without trying to visualize which way which gear is rotating as it was possible in case of simple or compound gear chain. So epicyclic gear chain we analyze rather mechanically. For that, first of all, let us derive what is the basic principle of analysis of an epicyclic gear chain. Towards that, we want to study the relative motion between 2, 3 and 4. And as I said, it has 2 degrees of freedom, so 2 input speed only, 2 input speed are necessary to fix the output speed. So what we do, we say we give input to gear 2 and gear 3, and what is the speed of gear 4. We prescribe the angular velocity of body 2 and body 3, and we want to find that of body 4. We want to study this relative motion. To study this relative motion without any loss of generality, I can take one body to be fixed, and let me take this body 2 is fixed. And then if I move, that means omega 2 I am taking to be 0. That is one input. And then if I know omega 3, the other input speed, the question is what is omega 4. To do that, let us say I give the arm a rotation theta. Link 3 has rotated by an angle theta. The center of this gear has come here, and this gear is taken up this position. This is the vertical line. Now this vertical radius after the gear has rotated has come here. This vertical radius has become this radius. So let me say this present contact point I call P, and this point I call Q, and this original contact point I call R. Theta is the rotation of the arm, and what is the rotation of gear number 4? This vertical radius has become this. So the total rotation of this is so much. Phi is the rotation of body 4, theta is the rotation of body 3, and body 2 is held fixed. Because these are fixed circles, that means one rolls over the other without slip. That means these two arc lengths must be same. This arc length on the smaller gear, planet gear, is same as this arc length on the sun gear or larger gear, because they are rolling on each other without slipping, because this represents the fixed circles of the two gears. So arc PR is same as arc PQ. Which means, if I say radius of this gear, fixed circle radius is RP2, and fixed circle radius of this gear I call RP4.
So rp2 into theta is rp4 into phi. Phi minus theta. Sorry. This angle is theta. If this angle is theta, the arm makes an angle theta with the vertical line. So with this vertical line, the arm makes an angle theta. So this angle is phi minus theta. Phi is the total rotation of gear 4 and theta is this angle. So this angle is phi minus theta. So this arc length PR is rp2 into rp4 into phi minus theta. Now what we shall see that the relative rotation of the gears with respect to the arm still follows the teeth law. That is, number of teeth inversely proportional to the number of teeth, which is appropriate sign. Let me say what is the rotation of the sun gear with respect to the arm. Sun gear was fixed, arm gear rotated theta in the clockwise direction. So rotation of 2 with respect to arm is theta but in the counterclockwise direction. Rotation of arm with respect to 2 which was fixed is theta in the clockwise direction. So rotation of 2 with respect to arm is the opposite of that, theta in the counterclockwise direction. And what is rotation of 4 with respect to the arm? Gear 4 has rotated by an angle phi in the clockwise direction. Arm has rotated by an angle theta in the clockwise direction. So rotation of 4 with respect to arm is phi minus theta in the clockwise direction. In the clockwise direction. Let me see again. Arm has rotated by an angle theta in the clockwise direction. Gear 2 has not rotated. So rotation of 2 with respect to arm is theta but in the counterclockwise direction. Rotation of 4 is phi, rotation of arm is theta, so rotation of 4 with respect to arm is phi minus theta in the clockwise direction. And because of these two arc lengths being equal, this is the relationship between phi and theta. So if I divide this by this, I consider rotation of 4 but with respect to arm, and rotation of 2 again with respect to arm. If I talk of these relative rotation and take the ratio, we are getting phi minus theta, that is in the clockwise direction, divided by theta, that is in the counterclockwise direction, so I put a negative sign. So we see that in this epicyclic gear train, the relative rotation of 2 gears with respect to the arm, if I write rotation of 4 with respect to arm divided by rotation of 2 with respect to arm is phi minus theta divided by theta, but this is clockwise, this is counterclockwise, so I put a negative sign. So from this equation, which I got by having these two arc lengths same, what I can write, this is equal to minus rp2 by rp4. Phi minus theta by theta is rp2 by rp4, and this is a negative sign. And this is same as minus number of tooths on gear 2 divided by number of tooths on gear 4. Because this is the pitch circle radius which are proportional to the number of tooths because they have the same module. So what we are getting that in case of an epicyclic gear train, because the arm is moving, the absolute rotation of 4 and 2 are not governed by that number of teeth on them. Otherwise it is exactly the same train value, only if we consider relative motion of 4 and 2 with respect to arm. Not the absolute motion, but the relative motion with respect to arm, that still follows the
chain value as minus because this is external gearing and inverse ratio of number of teeth. Rotation of 4 by rotation of 2 is minus N2 by N2. This forms the basis of analyzing epicyclic gear chain in a mechanical way. We have to only remember that it is the relative rotation with respect to arm follows the chain value given by the number of teeth. So this we put in a somewhat mechanical tabular method. What we will do, we first lock all the elements of a planetary gear chain to the arm. All the elements are locked to the arm. That means the whole thing becomes one rigid body. And we write condition, all elements, all the gears locked to the arm, which means the whole chain becomes one rigid body, and then give arm some y revolution. Then gears, all gears 2 and 4, because they are locked to the arm, under this condition, if I give arm y revolution, I will get y revolution to all the gears. And second condition I consider is lock the arm. That don't allow the arm to move. That means arm, these are revolutions of arm, gear number 2, gear number 4. Lock the arm, that means arm is not given any revolution, and give any x revolution to any of the gears. Say I give x revolution to gear 2. Then because the arm is locked, it is not an epicyclic gear chain anymore, it is just a simple gear chain. So rotation of 4 I can easily get as minus x into N2 by N4. Minus because it is external gearing and inverse ratio of the number of teeth. Then add these two, and that is what we get resultant motion. So here it is y, here it is x plus y, here it is y minus x into N2 by N2. Now as I said, it is a 2-degree freedom mechanism. To all the speeds can be, output speed can be determined only if you give me 2 definite inputs. That means 2 of these speeds must be known, then only I can determine the third. So I get 2 equations by equating the given speed, and I can determine x and y, and once I know x and y, I know the speeds of all the elements because they are all expressed in terms of x and y. Of course the number of teeth are given. This is the method that we shall follow, and I shall solve few examples to show how to use this tabular method for analyzing epicyclic gear chain. So let me now conclude today's lecture. What we have learnt is simple, compound and epicyclic gear chains. To analyze such gear chains, we found that analysis of simple and compound gear chains are pretty trivial. Only thing one has to be a little careful about the direction of rotation if there is an external gearing or internal gearing, and there are several numbers of intermediate shafts. But when we come to epicyclic gear chain, what we have noted that epicyclic gear chain has 2 degrees of freedom. Degree of freedom is 2, which means 2 input speeds need to be specified to determine all other output speeds. Conversely, if there is only 1 input, then I can get 2 outputs which can be adjusted because you have to follow one relation, but you cannot determine exactly what will be the output speed. That is the degree of freedom is 2, and which has a lot of applications as we will see later in our next lecture. To analyze this epicyclic gear chain, the only thing to note is that it is the relative rotation of the gear with respect to arm is equal to what we call the chain value. That is, as we get normally by in a simple gear chain or compound gear chain using the number of teeth. So it is the relative rotation with respect to arm is given by the chain value, not the absolute rotation ratio of two gears. Which means if I write to say speed of gear 2 minus speed of arm, small n refers to the RPM, by N4 minus N arm, where 2 was the sun gear, 4 was the planet gear, and N arm refers to the speed of the arm. Then this is for external gearing was given by N4 by N2. And we shall use this for a tabular method, which I also explained that we talk of two conditions. First, we lock all the elements to the arm, then give arm a particular revolution, then lock the arm and give one of the gears some other revolution and calculate what are the revolutions of all the elements. Then add these two, we get equations in terms of two unknowns, and two input speeds specified. We'll be able to solve for those two unknowns, and all other speeds are expressed in terms of those unknowns, so we should be able to determine those. This we shall see in our next lecture as examples, through examples.